Welcome back to Differential Calculus. In this video, I want to look at some operations on functions. Once again, this should be something that seems familiar to you, although I'm going to take it in a direction that you may not have seen in your previous mathematics courses, depending on what path you took to get to this course with me. Operations on functions are the same operations we see for other situations: addition, subtraction, multiplication, division. Functions have one other interesting operation called composition that doesn't exist on numbers on its own. And performing these operations is pretty straightforward. Right? I'm not going to try to insult your intelligence by telling you that if I have function f of x equals x squared and g of x equals x cubed, that it is in any way difficult to figure out that f plus g acting on x is simply the sum x squared plus x cubed. All right? That is all there is to operations on functions, except when it's not. Right. Things get a little bit trickier when I start looking at things in the other direction. And so, what I want to think about in this course is if I have something like f of x is equal to 3x squared sine x. It's not all that difficult once you know what you're doing, but getting into this habit of seeing it in the first place is challenging. When I see f of x equals 3x squared times sine of x, I immediately see, oh, there's an algebraic piece, 3x squared, and there's a trigonometric piece, sine x, and they're being multiplied together. So if I set one function, I'll use u of x is equal to 3x squared, and v of x is equal to sine of x, then f of x is equal to u times v acting on x. This is the direction that is more important at this point. Right? I expect you already know that if I gave you u and v in this form, you could multiply them together, you could get the thing that we started with. I want you to be able to look at the result, 3x squared sine x, and immediately your mind says, oh, that's two things multiplied together. This is a lot trickier, not because it's that much more difficult, but because it's that much more flexible. When I teach this face-to-face, I almost always have someone at this point interrupt me and say, well, why couldn't you have done that u of x is equal to x squared and v of x is equal to 3 times the sine of x? The answer is you absolutely could. This is equally valid. You can do it this way. You can do it this way. And either way will give you something to work with. Right. The goal here is the original function, 3x squared sine of x, is a complicated function. There's a lot going on there. If I break it down, each of these pieces is a simpler function than the one we had to start with. And simpler is the key. Simpler is what we're looking for. If I can take a complicated function and turn it into simpler functions, then I can work with these simpler functions on their own, and I can learn some rules for combining the results for the simpler functions to get the more complicated function. That's the big idea. That is a skill that we are going to use in just about every example for this entire course. So multiplying is one of the options. It's certainly not the only one. Related to that earlier example, just adding and subtracting is of value, but it's a little bit too limiting. And so we have this idea called a linear combination. And a linear combination is any constant a times a function u of x plus, or it could be minus, but we'll just bake that into the next constant I'm about to write, b times v of x. And if we can recognize that we have a linear combination, there's a lot of really powerful things that we can do from here. For anyone who is going to move on from this course to take a course in linear algebra is the study of linear combinations and the study of things that work very nicely when you recognize a linear combination. Right? So if I have a function like f of x equals 3x squared plus 5 over x, recognizing that this is a sum is not that challenging. From there, I can split things up further and call it a linear combination. My functions are u as x squared and v as 1 over x, and my parameters, my constants, are a equals 3 and b equals 5. Being able to split this up like that, taking a complicated expression, this one's not that complicated, and making it simpler is the entire goal. In function composition, that's where things really get tricky. I'm going to go through the details of function composition. Because the notation here is one that's not used all that often. And I'll be honest, we won't use it all that often in this course either. But the technical notation is that we have f small circle g, and we read that as f composed with g. F composed with g of x is the function f evaluated at the function g of x. And so if I have a couple of functions, say that f of x is the square root of x, and g of x is 3x plus 5, then f composed with g, evaluated at x, is simply the square root of 3x plus 5. And again, that is useful. That's hopefully something you've seen before. You may or may not remember dealing with that notation, that circle representing composition, but it is a concept you should have seen before. I always want to go through a couple of examples to lead off here, because one of the things that I want to stress is that function composition does not have a commutative property. If I take those two functions and I write them in the order, g composed with f of x, we're going to get a very different result. This is going to come out as 3 times the square root of x plus 5. And so depending on what you have, depending on what you're working with, sometimes you can think about the composition. Sometimes it's easy, sometimes it's a little bit more challenging. Let's go to one more example here. How about f of x is equal to 5 times the sine of x squared minus 1? When I see this expression, the thing that jumps out at me is that I have this expression, x squared minus 1, which is sitting inside of the argument of a sine function. So this is composition. My u of x is 5 times the sine of x. My v of x is x squared minus 1, and I have that f of x is u of v of x. Or if I want to write it more formally, this is u composed with v evaluated at x, but you know, the notation is not that important to me, either way you want to write it. One of the challenges, one of the places that I see confusion often is students looking at a situation of composition and trying to work with it as though it was the product of two functions, or seeing the product of two functions and trying to work with it as composition. So think about what the function is doing. X squared minus 1 is the argument of the sine function. The argument of the function is what you get when you're doing composition. If I just rearrange this just a little bit, 5 times x squared minus 1 times sine of x, now x squared minus 1 is something separate from sine of x. And in this case, I have u times v of x instead. Right? It's a subtle difference, but it is a difference, and it is something that will be confusing. We are going to see both of those frequently in this course. Paying attention to which one you have in each situation is definitely going to be something to slow down and make sure you're not making mistakes on. While I'm on the subject of operations on functions, I want to go back to the idea of transformations and show you one last one, the absolute value transformation. Absolute value transformations are transformations on graphs that occur when you perform a composition of a function with an absolute value function. Let's look at a pretty simple example. Actually, let me scroll down a little bit, get that page break off of the screen. Y equals x squared minus 4. This is a parabola. It's a parabola you should be pretty well familiar with from your previous mathematics courses. If I try to sketch out this graph, it is going to go through the point 0, -4, 1, -3, -1, -3, 2, 0, -2, 0. Now I want to graph y equals the absolute value of x squared minus 4. And once again, as I've said many times with transformations, you can work through this algebraically if you want to. It will absolutely work. But I find that it is far and away easier to try to think about this in terms of what is the function actually doing. What is absolute value doing? If the value of the function is positive, then the absolute value of the function stays exactly the same and nothing changes. If the value of the function is negative, then the absolute value takes that and makes it positive. And so when you have an absolute value transformation, you have a figure that looks like this. Imagine this, if you're having trouble seeing what happened. Take the x-axis and fold it in half so that everything ends up on the top and there's nothing left below the x-axis, right? Imagine that you drew this parabola on a piece of cellophane, a piece of transparent plastic, and then you folded that piece of plastic in half so you can see what is happening in the bottom half from the back, and you can see what is happening at the top half through the transparency. That is the transformation that we made here. That's the way I think about an absolute value transformation. When it comes to graphing things, I'm not going to be that worried about your ability to graph things by hand. We are frequently going to use computer software to generate graphs for us. I am a little bit more concerned about your ability to think about compositions and think about other transformations. So what I'd like you to do is look at this function. I should probably put an of x on that. F of x is equal to the square root of 9 minus the sine of x. I would like you to I would like you to determine which of the four operations makes the most sense for this particular function. Is this a linear combination of two simpler functions? Is this a product of two simpler functions, a quotient, or a composition? Then once you have that determination, name the two simpler functions. All right, take a couple of minutes, see what you can do with that one, and I'll see you in the next video.